Alright boys, welcome back to the channel. If there's any girls watching this, hey. Okay, so let's get into the problem. Three identical styrofoam balls with the same mass are suspended from a fixed point by three non-conducting threads, each with length 50 centimeters, and at equilibrium, the balls form an equilateral triangle. What is the common charge Q carried by each ball? So this should seem pretty intuitive, like there's three blocks with the same mass, same charge, and they're hanging from a string, so then since they're like charges, they'll repel each other and then settle into that equilibrium position, forming an equilateral triangle as the base. So it'll kind of look like a, what do you call it, triangular prism. So as we do with any problem, let's just draw it out first. So this is one of the charges. I can say that this is another one right here. There's another one here. And then, oopsie. Okay. So then they're hanging from some threads. Very nice. Then we're told that each thread is a length L. We're told the side length of the equilateral triangle. What else are we told? So we know that these angles are all 60 degrees. And okay, so what I'm going to do to solve this problem is just focus on one of the balls. And the reason being that the forces applied on each ball are the same, because each ball gets two electrostatic forces on it at the same angles, and then gravity, and then this tension force. So the symmetry is really useful here. So let's just begin by considering basic forces. So the first one is, of course, just gravity in this direction. And then we have the tension along this thread. Oops. Okay, along this thread. Now what I'm going to do to define my coordinate axis is say that the y-axis is the x component, where the horizontal component of this tension lies. So this is the x-axis, so I'll just go ahead and extend that. So now we have our x and y-axis. Just imagine that y-axis going up like that. And we can see that this tension force, since this is an equilateral triangle, and this is a triangular prism, we can see that this horizontal part of the tension force, where the x-axis is, bisects this angle right here, this 60-degree angle. So the angle on either side is 30 degrees. That'll be very helpful, as you will see very soon. So then we have tension, we have gravity, and then of course we have the electrostatic force from each ball. So from this ball there's an electrostatic force being applied along this side of the equilateral triangle, so that goes a little bit in this direction. So we'll just call that E1. And then there's also the electrostatic force from this one that goes along this side of the equilateral triangle. Now, as you can see, these forces have components in the x and z direction. And so we'll just deal with that in a sec. First, let's just look at the forces in the vertical direction along the y-axis. So we know that the net forces, the net forces in the y direction is equal to 0 because it's at equilibrium. And we can see that there's this gravitational force, and then there's the vertical component of this tension force. So what I'm going to do is I'm going to say that this alpha, right, this angle between the tension and the x-axis is simply alpha. So then we can go ahead and say that the forces in the y direction are t sine alpha minus the gravitational force, and from this we can see that tension is equal to mg divided by sine alpha. Now let's look in the x direction. So of course we know that this must also equal 0 because it's at equilibrium, and this will equal So what is going in the positive x direction? We see that these two forces both have x components, right? And since this axis is going through the bisector of this angle, and these are essentially just two intersecting lines, right, that intersect at this point, we know that this angle right here is actually equal to this angle right here because they're vertical angles. And then since this is a bisector of that angle, of this angle, it's also a bisector of this angle. So the angle above the x-axis at which this force acts is 15 degrees, and I mean 30 degrees, and then the angle here is also 30 degrees below the x-axis. So what this tells us is, since we also know that these two forces are equal in magnitude because they're the same distance away and these two carry the same charge, we know that the z components of these two forces cancel out. So we don't have to consider these z components. That's done. What about the x components? This force has an x component going this way. This force has an x component going this way. They're the same magnitude, so we can just say that the forces from the electrostatic forces from both of these is just 2 times the electrostatic force from one of them in the x direction, right? So we can say that this is 2kq squared over x squared, because cosine 30. Degrees, because this one would have exerted a force in the x direction of kq squared over x squared. Cosine 30, that's the x component, and then this is the exact same, so we just multiply by 2. Minus t cosine alpha, which is the extra component of the tension. T cos alpha. And then quickly simplifying, we get that Q is equal to the square, if we just take this tension and substitute it into this T right here, mg over sine alpha, we get that this is we simplify this expression to 2kq squared over x squared cosine 30 degrees is equal to mg over tangent of alpha. And then Q is simply equal to mgx squared all over 2k cosine 30 degrees tangent of alpha all square rooted. Now we're solving for Q, and we know all of these quantities except the tangent of alpha. So that's what we're going to solve for here, using a little bit of geometry. So I'm going to go about that is through the side lengths that we have. So I'm going to draw this line here right through the center of this equilateral triangle, and then this line here from the vertex to the center. We'll say this is D, we'll say this is H. Now we know that tangent of alpha is going to be equal to H over D, but we don't know what H and D are. So for D, we can solve that using the properties of an equilateral triangle. So if we look at the equilateral triangle base from above, so let's say this is the center, right, of that triangle. Let me draw it a little bigger. Say this is the center. We know that the center lies at the intersection of the perpendicular bisectors of each angle, right? We know that each side length is x. And so this length right here will be x over 2, right? Because it's, by definition, it's a bisector right here. It's bisecting it there. So then we're solving for this distance right here, d, right? Because this is analogous to the distance from here to here, here to here. Now this is x over 2, and we know that since it's an equilateral triangle, half of this angle will just be 30 degrees. So we can say that cosine 30 degrees is equal to x over 2 divided by d. So d is just equal to x over 2 cosine 30 degrees, which is just root 3. And then let's solve for h. To do that, we'll just use the Pythagorean theorem, because we know that this forms a right triangle. We know dh, and we know d and l, and we just have to solve for h. So then h is equal to root L squared minus D squared, which is just equal to root L squared minus X squared over 3. And so tan alpha becomes, tangent alpha becomes H over D, so that H is this, all divided by X over root 3. Simplifying, we get root 3L squared minus X squared all over X. Now we go back to our expression for Q, and we just plug this quantity in for the tangent of alpha, and we get root tangent of alpha is X, so then this X goes to the top, get mgx to the third, 2k, actually, we'll just evaluate. So this is root 3 over 2, so you just get k root 3 times root 3L squared minus X squared, all square rooted. And if I punch this into my calculator, I get that this is 2.05 times 10 to the negative 7 coulombs. And so a microcoulomb is 10 to the negative 6 coulombs. So then this is 2.05 times 10 to the negative 1 microcoulombs, which is just 0.205 microcoulombs. And that right there is your answer.